I'm Ollie Wright, UP2070883, and this is my submission for CT5MEGA. My artifact is a terrain generator that uses a Perlin noise algorithm to generate a terrain and manipulate a mesh to display that terrain in 3D. Additionally, it can just display the noise on a 2D plane. Features. My artifact has two modes that you can toggle between. One which displays an image on a plane of the noise that's generated, and one that renders the terrain into a 3D space. The algorithm used to generate both of these is fully customizable, so you can pass it the size, cell size, octaves, frequency, amplitude, persistence, and lasonarity. It also uses a seeding system for its randomness, therefore inputting the same seed will result in the same output, essentially procedural generation. Theoretically, through the system, infinite terrain could be generated, although it would repeat it at a really high period, as the seed is essentially just a randomized offset from that period. Before we go into the specifics of the algorithm, here are my rewrites of the inbuilt Unity functions, which have their own operations. Take note that not all of them are used within the project. They were implemented for the sake of potentially being used, but I couldn't find an appropriate place to put vector 4s or matrix 4x4s in the program without rewriting features or adding excessive new ones, other than one occasion which I'll mention later. Vectors are used extensively throughout the project, as the generator uses a Perlin noise function. This function operates by taking an x and y position and calculating the dot product between that and a corner where a unit vector of a random direction is, which is what the dot product is with. Here's the noise generation subroutine. It takes in all the parameters that it's meant to be using to generate the terrain, and then for each pixel in the desired output terrain or image, it will, for the amount of octaves, calculate the Perlin value of that position and then manipulate that by the frequency and the amplitude before mapping that to a height map. The Perlin function takes the decimal x and y position of an individual pixel within a grid of cells of the cell size specified by the function. It then uses dot product between the offset vector for a corner and a random unit vector generated at that corner. Note that the magnitude of these vectors is very important later, so you don't normalize them. This is then repeated for each corner. Here's the code for the vector generated at the corner. It takes in the x and y position of the cell, not the individual pixel, uses the function where it multiplies it by a random number and adds the seed, and then mods it by 1 to get a value between 0 and 1. This is used to seed the inbuilt random function within the system. Note I did try writing my own, but it tended to bias, so I stopped using it. It takes the value of the x and y position and applies smoothing effects to the values. Otherwise you'll end up with this quilt pattern as shown on the left. Then weights the influence of the dot product at this position from each individual corner by lerping based on the magnitude of the offset vector from the corner that has been smoothed. The final result of this is a float between 0 and 1, which is then appended to the height map. When generating the 3D terrain, the height map is then used to make a mesh. It iterates through each value in the height map and assigns that to a 3D space vector. Each vector is representative of a vertex within a 3D mesh, for which the triangles are then calculated and it is displayed to the user. It's then textured according to the height using this algorithm and displayed for this final result. To use matrices within my project, I implemented a function that marked the highest point with a billboard. It calculates the vector between the camera and the billboard before determining the relative right and up vectors. It then takes each vertex on the mesh and transforms them by a rotation matrix specified by the right, forward, and up vectors. And here's the code where you're multiplying a matrix 3x3 by a my vector 3, which essentially is a 3x1 vector, resulting in another 3x1 vector being outputted. Analysis. I chose to study a random noise function because I know it involved a lot of vector maths, interpolation, smoothing, and mesh manipulation. I settled on Perlin noise as it's very well explained and documented online. I also didn't want to hardcode any numbers and let the user customize whatever I made. Perlin noise can take a number of different parameters, all of which do slightly different things to the actual output of the generation. I chose Perlin noise specifically because it essentially serves as the backbone for a number of other similar noise algorithms, the kind that can be used to generate terrain. Other noise functions didn't employ the same amount of mathematical concepts as well. So Perlin noise used an extensive amount of vectors as well as interpolation. There are other noise algorithms that are less computationally demanding, such as simplex noise, but they produce kind of weird outputs which aren't necessarily natural in terms of terrain generation. So you'd end up with what is essentially very high frequency, high amplitude noise. Smoothing was used alongside lerping to remove artifacts from the image. You can see a very clear grid pattern on the left side, while the smoothing function removes this from my generation on the right hand side. I chose to implement billboarding with matrices as it's an efficient way of rotating a given set of vertices when given two matrices, which, as I explained earlier, the vector 3 is the equivalent of a 1x3 matrix. An alternate solution to the billboarding could have been to employ quaternions. These are slightly faster and also don't suffer from gimbal lock like matrices do. However, simply I couldn't understand them, and I felt it was a lot easier to implement matrices. So what could I have done differently within the project? I have a lot of unused functions and classes within the project, such as my matrix 4x4, which has a lot of definitions for matrix multiplication, translating, scaling, and inversion. However, I couldn't implement them effectively within a time constraint without extensively rewriting functions. Another system I'd remake if I redid the project would be the camera system. It currently, regrettably, uses the inbuilt Unity quaternion and lookout functions. I tried to code an implementation of these myself, but I really couldn't work out how to effectively put them into the project without creating a whole myTransform class, which would have been weeks worth of work. I'm sure there was a more efficient way to do this, but I couldn't figure it out. Reflection. Over the course of development, I had a number of small issues and a couple of large issues that I faced. The first was my smooth step was returning incredibly high values, and it just didn't seem right in my original implementation. I ended up rewriting my code so that the only integer coordinates were at the corners of the grid cells. This then resulted in the offset vectors only ever being decimals, and therefore adhering to the smooth step requirement of the value inputted being less than 1. I also had a problem with my texturing, which was appearing just grey at first, although the mesh was generating completely correctly. I ended up having to research UVs and how they worked. This then allowed me to recalculate all my UVs and match them to the size of the plane by scaling them all, as you can see when I divide by UV scale. My biggest problem was when I originally created the function, I wrote it to run on a 64 by 64 grid. I always had the intention of making it editable, but originally I wrote it for that, and I never tested any other cases. I realized that the way I was originally performing the function wasn't viable, as it used an approximation when I was recalculating where to put the calculated height map into the height grid, as height grid's indexes were all integers and the cells were floats. This then caused me to have to rewrite the function that gets the random vectors in the corner. It originally called just once to generate a grid of random unit vectors of the given size divided by cell size, but I rewrote it to be procedural based on the x and y position of any given cell corner. A limitation is that it's called multiple times while feeding it the same values. The next step would be to maybe create some form of data structure that could hold these after they've originally been generated, so it doesn't run through generating them again. Fun bonus, this took me half an hour to fix. Pause it and see if you can figure out the problem. One problem that I had that I didn't manage to implement a solution of was the aforementioned problem with the camera. It wasn't so much a problem as I was using Unity's default implementation, which I really should have written my own versions of. But unfortunately, after trying matrices, quaternions, as well as Euler angles, I couldn't get the camera working. This is where the gutted carcasses of the dead data structures comes from that I showed you at the start. Potential improvements to my project could be to deal more with matrices. Maybe I could use them to scale, rotate, and transform the geometry. For example, putting two meshes together stitched by a lerp function that uses translate, rotate, scale functions to match the edges of the mesh together by making them the same size and rotation. I could implement more Euler calculations, as the artifact currently doesn't deal with a huge amount of them. I mean, the functions are there, they just don't get used. A more advanced function within the program that I could have implemented would be, say, calculating the gradient of some part of the ground, and then using a matrix transformation on a ski lift prefab to see if I could place it on the side of a mountain with a steep gradient. I could also include some kind of a biome system where each has their own type of terrain, and also generate shrubbery or trees using Poisson disk sampling, which is another type of pseudo-random noise generation. This project has helped me a lot with my ability with complex vector maths as well as procedural generation. Mesh manipulation was new to me, and I've employed it to, I think, pretty good effect. Maybe in the future I could add a collider onto this mesh and have it as a playable open world. Using matrices to calculate the billboarding did take me a long time to get working, as I really wasn't very confident with them going into the project. But I am happy with how it came out, and it works as intended. In conclusion, I'm pretty happy with how it came out, and I've greatly improved a number of my abilities, but I definitely could have used more advanced functions such as collision or quaternions, and I should also clean up the project as to not include some random redundant structures and methods like my vector 4 and my matrix 4x4. Thanks for watching.